All right, today we're going to add to our huge list of trigonometric identities with even more identities. Today we want to look at sum and difference identities, where we have cosine of a sum or cosine of a difference. So let's just start by writing them down. Your textbook does a pretty good job of deriving where these come from. So I'm less worried about that and more worried about getting right to what we want to remember. So the cosine of a plus b is the cosine of a times the cosine of b minus the sine of a times the sine of b. Now, at this point in your mathematical career, you could just start here. Cosine of a plus b is cosine of a, cosine of b minus sine a, sine b. So the functions go together, but the operation is opposite. Because when we have cosine of a minus b, it's the cosine of a times the cosine of b plus the sine of a times the sine of b. Now, this is going to be difficult to remember, but there are patterns involved that will help. And the more important thing to remember is that there are such a thing as sum and difference identities. So if you can't remember, is cosine the one with the cosine, cosine, sine, sine? Is that the one with the same sign or the opposite sign? Knowing that they're called sum and difference identities, you could put that into Google and then you'll be able to look them up. But you have to know they exist to bother looking them up in the first place. So we also have sum and difference identities for sine. So we want the sine of a plus b and the sine of a minus b. The sine of a plus b is sine a cosine b plus cosine a sine b. Sine a cosine b plus cosine a sine b. An alternative would be to go, so the pattern here, we've got AB and then AB, and maybe you like to follow that consistent pattern for the rest. But that means that sine goes sine, cosine, cosine, sine, whereas the cosines are cosine, cosine, sine, sine. Also notice that the sum identity for sine has the same sign, it's plus. The difference identity for sine is a minus. Lots of pattern available to help you remember which one goes with which. Of course, we also have sum and difference identities for tangents. And once again, it's easy to find the sum and difference identities derived for cosine, for sine, and for tangent. For tangent, we could just combine our cosine and sine sum and difference identities with our ratio sum and difference identities, and then just hit them with the algebra stick for a little while. Or we can just remember that the tangent of a plus b is the tangent of a plus the tangent of b over 1 minus the tangent of a times the tangent of b. And there's a difference formula for the tangent as well. That says the tangent of A minus B is tangent of A minus the tangent of B over 1 plus the tangent of A times the tangent of B. This only seems like a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. Or remember that such a thing called sum and difference identities exist, and then you can go look them up. But like I said, you have to know they exist to go look them up. Notice that tangent, the form is the same. There's a tangent of A plus or minus the tangent of B, and then it's 1 minus or plus the tangent of A times the tangent of B. So notice that the top matches and the bottom is the opposite. Now, one of the types of problems that we typically see when we're learning these identities is, say, find the exact value of, say, cosine of 75 degrees. Now, we might not know the exact value of cosine of 75, but we do know the exact values of cosine of 30 and cosine of 45. And so we're going to express 75 as 30 plus 45. So I'm going to read 75 as 30 plus 45. Because these are cosines and sines that we do know. So we'll say the cosine of 30 plus 45, I'm going to regret color coding this in a minute. Is going to be the cosine of 30 times the cosine of 45 minus the sine of 30 times the sine of 45. And the reason that we do this is because these are all values that we know. These are exact values that we know. Cosine of 30 times the cosine of 45, sine of 30 times the sine of 45. We know that the cosine of 30 is root 3 over 2. Sine of 30 is a half. Cosine of 45 is root 2 over 2. Sine of 45 is root 2 over 2. And we just multiply and subtract. So here we'll get root 6 over 4 minus root 2 over 4. And we can write that as one fraction, say root 6 minus root 2 over 4. And there's the exact value. There's the exact value of the cosine of 75 degrees. Now, when you're faced with this kind of exercise, we're not doing this because we need to know the exact value of cosine of 75 degrees all the time. The point of this exercise would be to make us look at the 75 and remember that we know the cosine and the sine of 30 and 45 and see the 30, 40, and 45 in the 75. If I really needed to know what the cosine of 75 was, I probably wouldn't really care that much about the exact answer. I'll just switch my calculator to degrees and say, hey, calculator, what is the cosine of 75? Although it'd be useful to find out the square root of 6 minus the square root of 2 and divide that by 4. Oh, good. That means I remembered things correctly. So here's a list of what we call sum and difference identities. It's how we find the cosine, the sine, or the tangent of a sum or a difference. So let's see where these can lead. One type of identity that is really useful are double angle identities. It seems crazy to go on right on to the next category of identity without spending more time on these sum and difference identities. But that's okay, because the double angle identities are going to be, we're going to derive them from the sum and difference identities. So what we're going to do is we're going to take the sum identities and just make A equal to B. We're just going to use the sum identity and make A equal to B. So remember that the cosine of A plus B is the cosine of A times the cosine of B minus the sine of A times the sine of B. Yeah, I'm already remembering it. And I'm just going to replace B with A. So I'm going to have the cosine of A plus A. So that'll be the cosine of A times the cosine of A minus the sine of A times the sine of A. So we get cosine squared A minus sine squared A. And that's the and cosine of A plus A is cosine of 2A.
Quick question: how did B become A?
To get the double angle identity, I replaced the B with an A so I can get A plus A or 2A. I wanted this to say the cosine of 2A. So.
Oh, okay. You just replaced it. Okay.
Yeah. And we'll let B equal A for the double angle identity. And so here is a double angle identity for cosine. We derive this from the sum identity for cosine. So not only can we get the double angle identity for cosine from the sum identity for cosine, this will also help us remember the sum identity for cosine. One of them might be easier for you to remember. And if you remember that the cosine of 2A is cosine squared minus sine squared, that'll help you remember that the sum identity for cosine is cosine, cosine, sine, sine, and it has a minus in the middle. So knowing this supports the thing that we knew before. We want to make connections between all these things. That will help us remember. An interesting thing to note with the double angle identity for cosine is that it leads to cosine squared and sine squared. And if we remember our Pythagorean identities, remember that cosine squared is 1 minus sine squared. So if I replace this cosine with 1 minus sine squared, we end up with 1 minus 2 sine squared. And so there's another double angle identity for cosine. Cosine of 2a is 1 minus 2 sine squared a. And now we're using this identity to help reinforce our memory of the Pythagorean identity. Hopefully you saw this coming, because cosine squared is 1 minus sine squared, but also sine squared is 1 minus cosine squared. So sine squared a is 1 minus cosine squared a. So if I replace this sine squared with 1 minus cosine squared, I get cosine squared minus, there's more than one term, so I'm going to put it in parentheses, 1 minus cosine squared a. I use the distributive property because this minus in front of the parentheses actually represents multiplication, so we're okay with that. So we'll have cosine of a minus 1 plus cosine squared a. So cosine of 2a is also equal to 2 cosine squared a minus 1. For those of you moving on into calculus, in Cal 2, this is very important because cosine squared is kind of a pain in the butt. Having powers of trig functions is kind of troublesome when it comes to integration, but integrating something like cosine of 2a is super easy, barely an inconvenience. And once again, we're reinforcing all of our trig identities into one big picture and not a bunch of little pictures. Let's take a look at a double angle identity for sine. We're going to do the same thing. I'm going to start with the sine of a plus b, which was the sine of a times the cosine of b, plus the cosine of a times the sine of b. And we're going to let b equal a to make a double angle identity. Because I want to know what the sine of 2a is going to be. So I'm going to let b equal a so that my sine of a plus b looks like sine of a plus a, which is also the sine of 2a. So sine of a plus a, using our sum identity, will be the sine of a times the cosine of a plus the cosine of a times the sine of a. So the sine of 2a is 2 copies of this sine a cosine a. And there's a double angle identity for the sine. This one doesn't involve sine squared or cosine squared, so I'm not going to do my Pythagorean identity stuff with it. But this will help reinforce which one is which when it comes to the sum identities for sine and cosine. Now we know that the cosine of the sum has the minus between the terms, and the sine of the sum has the plus between the terms. Also, because the cosine of 2a involves the cosine squared, that's the one, cosine is the one with the cosine cosine. sine, sine, and sine is the one with sine, cosine, cosine, sine. So by looking at these identities, we're reinforcing our memory of the previous identities. Because I can't let things go, and we've done 2 of them, we have to do the 3rd one. It's just my personal inability to let things go. So the tangent of A plus B, we have this fraction. The top matches, it's the tangent of A plus the tangent of B. And then the denominator was difference, 1 minus tangent A times tangent B. And we're going to do the same thing. We're going to replace B with A to get a double angle identity. And I'm going to write the tangent of A plus A, because I want to write the tangent of 2A. So we end up with the tangent of A plus the tangent of A over 1 minus the tangent of A times the tangent of A. When I add 2 things that are the same, I just have 2 of them. So it's 2 tangent A. And when I multiply 2 things that are the same, I square it over 1 minus tangent squared A. So there's our double angle identity for tangents. Any questions? So I find the double angle identities the easier ones to remember. But I have this relationship between, say, the cosine of 2A and the cosine of A. I also have a relationship between the cosine of 2A and the sine of A. So a double angle identity, if we turn it around and go the other direction, is also a half angle identity. So half angle identities are just going to be double angle identities in the other direction. So if we know, I'm going to use the cosine one. So if we know that the cosine of 2A is 2 times the cosine squared of A minus 1. I'm going to use the, oh yeah, I did write it right. I thought I wrote it backwards for a second there. 2 cosine squared A minus 1. So notice that A is just half of 2A. A is just half of 2A. So let's notice that. A is half of 2A. So if I replace A with half of A, or A with, cut A in half, I'm going to let I'm going to replace 2A with some other value, K. I'm just going to rename it as K. I can write the cosine of K is 2 times the cosine squared of K over 2 minus 1. Then I'm going to solve this for the cosine of K over 2. This is because we want a half angle identity. What if I have the cosine of half of an angle? So let's just solve. If I want to solve for cosine of K over 2, I'll add 1 to both sides. We'll divide by 2. And then we'll take the square root. So we have a half angle identity that says cosine of K over 2 is plus or minus the square root of cosine of K plus 1 all over 2. In solving, we had to take a square root, which meant we introduced a plus or a minus. The plus or minus will depend on the quadrants of K over 2. So the plus or minus is determined by the quadrants of K over 2. For example, one way we could use this is if we wanted to find, this is the contrived thing. This is just us making stuff up saying, look how useful this identity would be. Let's suppose that we wanted to find the exact value of the cosine of 15 degrees. Now we don't know the exact value of cosine of 15 degrees because for some reason we've agreed not to look at Wolfram alpha and just say, hey, Wolfram alpha, what is the cosine of 15 degrees? For some reason, we've decided to play on hard mode, and so we're not allowed to do that. But we will notice that cosine is 15 is half of 30. So the 15 is 30 over 2. So if I want the cosine of 15, I can use the half angle identity, and then that would involve cosine of 30, and we do know that one. So the cosine of 15 degrees is plus or minus the square root of cosine of 30 plus 1 over 2. Now we have to decide if we're using plus or minus, and we're going to use plus because 15 degrees is in the first quadrant. And cosine is positive in the first quadrant. Now we just replace cosine of 30 with root 3 over 2. That's what cosine of 30 is. And we just got this messy fraction to simplify. We can divide both of these by the square root of 2, or sorry, the 2. I'll distribute the 1/2 is what I'm thinking of. Root 3 over 4 plus 1/2. Oops. Any questions? Similarly, we could use the double angle identity for cosine that tells us about sine to solve for sine of k over 2. And we have a double angle identity for tangent. That one's going to be a lot messier, because we not only have 2 tangent a on top, we also have that 1 minus tangent squared a in the denominator. Any questions? So technically, I talked about 3 sections today, but all 3 of those sections are really closely connected. The sum and difference identities are kind of where we started. The double angle identities is where we got from the sum and difference identities. And then the half angle identities we got from the double angle identities. These things are all connected. And the reason I go through all 3 of these sections, just listing off the identities, rapid fire style, is that they're all connected. And knowing one set will reinforce remembering the other set. We need to look for those connections with all the different sets of identities. This will help us remember them later on. But like I said also at the beginning, the most important thing to do is remember that these identities exist. So if you can't remember the details, you will at least know what to drop into Google. So if you just go into Google and be like, all double angle identities. The first image that shows up has all of them. Actually, I don't like the first one. It derives them. The second image that shows up just lists them, which is what we needed. Any questions? All right.
Just a clarifying question.
Yes.
The square root of the square root of 3 over 4 plus 1/2 is the answer to a cosine of 15 degrees.
Yes.
Okay. And so when you put that plus signified what again? It was
the red plus.
Yeah, the red plus.
The red plus. Remember the cosine. When we solve for cosine of k over 2, we did a square root, and that puts a plus or minus in play. But the plus or minus is just going to be dependent on the quadrant that we find k over 2. since we're finding the cosine of 15 and 15 is in the first quadrant, we know we need to use a plus.
Oh, since 15 is in what quadrant again? Sorry, my bad.
15 degrees is in quadrant 1.
Oh, so it would be a positive because
And so it's
cosine
positive.
is positive, so it's positive. Okay.
Yeah.
And
So
then what?
if, for example, we were using this to find the cosine of 110 degrees, that 110 falls in the second quadrant, and so we would use the negative square root. I totally missed on that one because we don't know 100 double 110 is 220. We don't know that one. So 240 cut in half is 120. The cosine of 120 is one that we know. That would be a good way to check to see if this is.
And what if it was 270? Because that lies between the third and fourth quadrant. So would it be positive and negative?
So cosine of,
Sorry, my bad.
if we wanted to do the cosine of 270, that would be the one that we know. We know our cosines and sines and tangents of all the angles that fall on quadrants. So we wouldn't have to view 270 as being half of something. We just know that the cosine of 270 is 0. So that one is just no. This is for finding ones that we don't know, that don't fall on a quadrant, or for angles that don't have a 30, 45, or 60 degree reference.
Oh, we can just find by looking at the chart.
Yeah, if it falls on a quadrant or has a 30, 45, or 60 degree reference angle, then we already know what the value is. This is for angles that don't have a 30, 45, or 60 degree reference.
Oh, okay. And the reason I noticed that you put it's k over 2, so for cosine, so it's k over 2. So you don't need to put the 15 degrees over 2?
No, the 15 degrees is k over 2. 15 degrees is 30 degrees over 2. So the k itself is 30.
Oh, okay. Oh, okay. Got it.
Any questions? Any other questions? All right. So your job is to start off to learn these identities. You don't have to memorize them. A good exercise would be to just start by writing them down, even if it just not from memory, even if it just means putting a piece of paper on the left and putting a piece of paper on the right and copying it down and labeling it half angle identities, labeling double angle identities, labeling it sum and difference identities. It's really important that you write it down, like with a pen and paper. That helps you remember things better. A lot of times I'll see students in class taking notes with a computer, but the way that your brain operates when you're typing is very different than the way that your brain operates when you're writing. So if you are able to write, then that's a better way of taking notes during class. The other thing I see people doing during class, especially in math class, is just writing down whatever gets written on the board. That's not a good way to take notes either. You're not trying to replicate the notes on the board. You need to write down the things that you need to write down. It's especially the case here. I don't know if anybody's taking notes because I'm just posting them. But even when we get back in person, I'm still going to be posting the notes, but people are still going to try to write down everything that I write down. But they'll write down nothing of the things that I say. It's really weird. I think we need to have a class on how to take notes. It's not just taking dictation and writing down everything that I say or write down. You know what I mean? All right. That's going to do it for today. I just wanted to put these 3 groups of identities in front of you. That's going to do it for today. That's going to do it for this week. Everybody have a good weekend. I'll see y'all on Tuesday, and thanks for playing.